Lesson 11.3, Cross Products. Right, if I is a unit vector in x, and j is a unit vector in y, and k is a unit vector in z, meaning they're in that direction but have a length of 1 unit. And so we could say u is u1i plus u2j plus u3k. So this is the x, the y, and the z components. This is the x, the y, and the z components. The cross product can be found by using this determinant, where I have the I, j, k across the top, then u1, u2, u3, and then v1, v2, v3. This is different from the dot product. The dot product gave you a single number as an answer. This cross product gives you a vector as an answer. So these are the two vectors. Find the cross product. All right, u cross v, I, j, k. The first one, the second one. To find the determinant, copy the first two columns. So I have 3i plus a negative 3j plus 4k minus, because they're going up, 3k minus 6i minus negative 2j. If we collect like terms, we've got 3 and a negative 6, that's negative 3i. For j's, looks like I have negative 3 plus 2, which would be negative 1. And then for the k's, I have 4 minus 3 or plus 1 k. So translate to negative 3, negative 1, 1. There's several properties of cross products. First one, if you reverse the order, then it becomes negative. It does have a distributive property. So on this one, we're multiplying. This is multiplying. This is not distributive. This one's distributive because it's add. This one is not distributive because it's all multiplying. We have a multiply and a multiply. You multiply 3 things, you just multiply 2 of them, and then the third. But you could change the order, so the c could be multiplied with the v instead of the u. If you cross product a unit with itself, you get 0. Therefore, if you cross product 2 vectors and you get 0, then they are parallel. If you dot product with a cross product, we have the associative property. So remember, you have to do the cross product first so that you get a vector, because the dot product gives you a scalar number. The cross product is orthogonal to u and v. It follows the right-hand rule. So if we have vector u and vector v, if you take your right hand and curl your fingers from vector u towards vector v, your thumb is going to point towards the direction of the cross product. So this is your hand, your fingers, your thumb points the direction of the cross product. And the magnitude of the cross product is the same as the magnitude of u times the magnitude of v times sine of the angle between them. Another property of or use of cross products is to find the area of a parallelogram. The area of the parallelogram is base times height. Well, if I use vectors u and v to represent sides, I have an angle here, we can use this right triangle, and we know the opposite side and the hypotenuse, which would be the magnitude of u. So sine would be opposite over hypotenuse, or h would equal the magnitude of u times sine. Well, the base is just the magnitude of v, so our area is the base times the height, or uv with the magnitudes times sine of theta. But that is the cross product. So the area of a parallelogram is the magnitude of the cross product, where u and v represent adjacent sides from a single point. Another thing we have, if we have a dot product with a cross product, we have what's known as the triple scalar product. And a shortcut is to just do a determinant where the three vectors are all rows on the determinant. How is that useful? Well, it turns out the volume of a parallelepiped, which is the 3D parallelogram, such as in the picture, is the magnitude of the triple scalar product, where u, v, and w represent edges. So this would be u, v, and w.